Congratulations, ladies and gentlemen, you have done it. You have finished physics class. Almost. There's still this giant thing in the way. It's called an exam. So, I decided rather than putting together a multi-hour single review session, I'm just going to produce a series of videos on different topics that should hopefully help out. A little bit about your exam. There is a 3-hour time limit. You'll basically come to Gov School that morning and immediately come to physics, and then you'll have the entire morning at Gov School to work on the exam. There will be 30 multiple choice questions, each worth a point, one lab-based question, and this is not going to be anything too overly complicated, just to see, were you around during labs? And then 1 or 2 diagrams or concept-based free response questions that won't involve any calculation. That'll be 10 points each, and then I will produce 10 free response questions. It'll be up to you to respond to 8 of them, and you choose which 8. Now, once again, you are more than welcome to attempt all 10. Just make sure you let me know at the very end which 8 you want me to grade, and I will hop on and do that. You're allowed 1 sheet of paper of handwritten notes. This says 8.5 by 11, but if you'd rather, I've got slightly longer sheets on the physics platform that you are more than welcome to use. Now, you're allowed a graphing calculator. I know a lot of you don't have your own calculator, which is fine, but please do let me know before the day of the exam if you need one. On standard test days, it doesn't really matter if you ask for it the day of, but when it's the exam day, there's going to be 85, 86 students all crowded around the physics platform, so it's going to kind of be difficult for me to run back and forth with individual requests. So if you tell me beforehand, I'll have a calculator waiting for you with your name on it, and I will just give it to you when you come in. And that'll make things go a lot more smoothly. Plus, we only have a limited amount, so if you let me know ahead of time, then I'll be able to be sure that there's one reserved for you, rather than scrambling the day of the exam. Now, this document, this PowerPoint, really only serves as a menu of concepts. I'm going to just roll through these concepts. It's not designed to do your studying for you, basically. You still need to go back. You can look at a menu all you want, but until you taste the food, you don't know exactly what you're getting. So, use this to figure out your areas of strength and weakness, and use it to help you inform where you best need to study. Now, we started with units. So, some of you all, kudos to you, have gone all year without learning your metric prefixes. I'm not sure how, but you are going to need to know them directly on the exam. So, be sure that you've gone back and studied those, and that you know how to convert back and forth from one to the other. One helpful tool could be the metric staircase. You may use it, you may not. But this, once again, just shows you how many places to move your decimal point, left or right, if you're converting from one place to another. So that should help a little bit here and there. You're also going to need to know a good deal about vectors. So make sure you know how to break a vector into its x and y components. Make sure you know how to add vectors. One direction is positive, one direction is negative. Break it into x's and y's, add up your x's, add up your y's, bring it back together with the Pythagorean theorem. For this, you're going to need to basically have mastered SOHCAHTOA, as well as the Pythagorean theorem. Go from a full vector to its components, go from a component to a full vector, all that kind of good stuff. And then we started the semester with electrostatics. So every single proton and every single electron has a certain charge, except one is positive and the other is negative. And that charge is known as the elementary charge, has a magnitude 1.6 times 10 to the negative 19 coulombs. So they have the same magnitude charge, opposite sign, but they have way different masses. Sometimes you'll just see this denoted as a little e. Now, I'm going to give you that 1.6 times 10 to the negative 19 coulombs number on the exam. But just like on all the tests, I'm only going to mark it as the elementary charge is this. You have to know what the elementary charge actually means. Neutrons, by the way, have no charge, hence the name neutron. A few other things you need to know about charges. All charge is quantized. That basically means that I can have one excess electron or two excess electrons or three excess electrons, but I'm not going to have 1.5 excess electrons. Yeah, so it's all going to be integer multiples of that elementary charge. So 1 times 1.6 times 10 to the negative 19, 2 times 1.6 times 10 to the negative 19, all that. Charges are also conserved. That basically means I'm never going to gain or lose charge without transferring it somewhere else. And also, if an object is neutral, that just means it has an equal number of protons and electrons. Doesn't mean it has no charged particles making it up. So the way to get it charged is to either add or remove electrons. And there's a wide variety of ways to do that, depending on if that object is a conductor or an insulator. So the total charge of a closed system, that means nothing's allowed to enter or leave the system, that's going to remain constant at all times. We talked about how charged particles interact with each other. That's Coulomb's law, where F equals K times Q1 times Q2 all over R squared. One common mistake is this value R right here. A lot of people see R and immediately think radius, so divide any distance by 2. And that's not the case. In this equation, R is simply the distance from one charged object to the next. That's going to be measured in meters. K is 9 times 10 to the 9th Newton meter squared per Coulomb squared. And each Q is the charge of each individual object. Q1 is the charge of object 1, Q2 is the charge of object 2. Now, note that any force exerted between objects, both objects feel the exact same force, because K Q1 Q2 over R squared is exactly the same as K Q2 Q1 over R squared. Also, Newton's third law says any force produces an equal and opposite reactive force. So hey, it works with fall semester stuff too. Magic. Now, when I'm solving a problem using Coulomb's law, I like to follow these steps. Number 1, ignore any sign, and by any sign I definitely don't mean scientific notation. That changes the value dramatically. By ignore any sign, I basically mean if there's a negatively charged particle, don't worry about that negative up front. All that's going to do is inform you whether or not it's an attractive or repulsive force. Use Coulomb's law to figure out the magnitude of the force. Remember, force is a vector. Every vector has magnitude and direction. Coulomb's law gives me magnitude only. Then you can figure out the direction for yourself. Is this particle being directly attracted to the other one, or is it being directly repelled by it? And positives repel, negatives and negatives repel, positives and negatives attract. That's about it. Then there's grounding. So the ground is considered to be an infinite well of positive and negative charges. And as long as conductors are connecting to the ground, then electrons are free to come and go as they please. So you can use this to either charge or discharge an object, and I'll talk about how that works in a little bit. Polarization is a concept that is essentially just a separation of charge. Now, both insulators and conductors can get polarized. The insulators, however, the electrons are not free to move around the entire object. They're just free to move around their individual little atoms. So, if an insulator is getting polarized, that just means the electrons are going to one side of the atoms or the other. Fairly minimal effect. Now, conductors can get polarized on a much larger scale because the electrons are free to move around the surface of the conductor. They'll either go to the far side or the close side. But there's a bunch of ways to cause objects to get polarized. Most commonly, you'll bring a charged object near it. I mentioned this briefly last slide, but make sure that you know the difference between conductors and insulators. A lot of it is the same, but there are just a few key differences. They're on this chart here. Make sure you know those. Now, there are two different ways to charge conductors. There's conduction and induction. Conduction means contact. Conduction, contact. Conduction, contact. So the electrons, so basically you're touching, an uncharged conductor with a charged object. That contact allows the electrons to flow onto the conductor, and it will become charged. Or they can flow off of the conductor. Just depends. Induction is charging by trickery, and I did this with a few different Van de Graaff spheres. Basically, you bring a charged object near an uncharged conductor, and then you can give the electrons out, a way out, either by connecting it to the ground, by connecting it to some other object, something like that. And you end up with opposite charges. So, here's a little picture of conduction. Nice, direct contact. Cool. Go ahead and pause this and read the captions if you'd like to learn a little bit more about conduction. Here's an example of conduction, except with a positive object. Go ahead and pause it and read the captions there if you want to as well. Now, induction, this is the grounding example. The person's hand is basically being used as the grounder. You just hold a charged object near the conductor, that conductor becomes polarized. By connecting it to the ground, electrons will either escape if the charged object is negative, or more electrons will pile on if the nearby charged object is positive. Either way, you end up with a sphere that is oppositely charged the initial charged object. Sometimes you don't have to use grounding at all with induction. You can just put two conductors together, let them become polarized as a system, because electrons are free to flow from one object to another if they're in contact. Then separate them, and all of a sudden you've got two differently charged spheres. Cool. We then moved on from forces to talk about electric fields. These are pretty much just maps of forces that a positive charge would feel. So it's not a depiction of the path that the particle will follow, it's just at every point in time, well, every point in space, what direction and what strength force is that positive charge going to feel per coulomb of charge. Because it's a positive charge, it points away from positive and toward negative charges. So, we've been using the equation just of a point source, and that equation is the electric field equals K, which is still 9 times 10 to the 9th, times Q, where Q is the charge creating the electric field, not this little positive test charge that I'm talking about. Don't even worry about the charge value of that thing. That's just to help with the concept of what an electric field is in the first place. R is the distance away from the charge that you want to measure the electric field, and E is the electric field strength, which once again is in units of newtons per coulomb. That will tell me for every coulomb of charge I put here, how many newtons of force will it feel. So, once again, both forces and fields are vectors. Like I mentioned when I talked forces, you want to ignore negative values at first, figure out the absolute value of the magnitude, figure out the direction for yourself. With forces, either attractive or repulsive forces. With fields, you're going to want to figure it out essentially as by thinking about whether the source charge is positive or negative. Field lines point away from positive and toward negative. We talked voltage. Now, voltage is simply the amount of energy per coulomb of charge. So electric field is the amount of force per coulomb of charge in a little area of space. Voltage is the amount of energy per coulomb of charge in a region of space. So you can find the voltage due to a source charge Q, as just K times Q over R. And that's it. What's really nice about voltage is that it's not a vector, it's a scalar. So, unlike my advice for forces and fields, with voltage or energy, you cannot ignore negatives, solve for just the values, positive or negative, and that is it. If you've got multiple charges, then each one contributes a certain voltage, positive or negative, add up all those numbers, and that is it. That's the overall voltage at that point in space. So, quick reminder about vectors versus scalars. If you're dealing with electricity and it starts with an F, forces or fields, it is a vector. The scalars are energy and voltage. So take a look at this list and make sure that you treat vectors and scalars appropriately. Then we closed off this unit talking about capacitance. So Q equals C delta V. That means charge equals capacitance times the change in voltage between the plates. So as a reminder, a parallel plate capacitor has parallel plates. One plate will gain a positive charge, one plate will gain a negative charge, but the absolute value of the charge on each plate is the same, and that's defined as Q. A common mistake, once again, is because there are two plates, a lot of people want to divide Q by 2 or multiply Q by 2. Forget about that. Q is just defined as the magnitude of charge on one of those plates, and that's what's used in the equation here. C is the capacitance, that's just the ratio between charge and voltage, and delta V is the change in voltage between one plate and the other. Right? That's about it for electrostatics. Tune in next time when we will talk DC circuits. Yes.